Hi class, this video is on topic B9, head-on elastic collisions and collisions with cushioning. So we're going to continue working on the learning goals from our previous video, except for this video we're specifically going to look at solving problems where there's a head-on elastic collision and collisions where there is a bumper or a spring to cushion the impact during the collision. So in the previous videos, we've learned about the ideal cases of perfectly elastic or perfectly inelastic, and that in both cases, momentum is conserved. So momentum is conserved in all of those collisions. In a perfectly elastic collision, kinetic energy is also conserved. So the sum of the kinetic energies before an elastic collision is equal to the sum of the kinetic energies after. So this is unlike in inelastic, where kinetic energy is not conserved. So when we're solving problems involving elastic collisions, sometimes all we needed was the total momentum conservation equation. And we could simplify or factor, or it could become more simpler, or we had all that we needed just based on this equation. In other problems, more recently, when we have two unknowns, we also needed the total kinetic energy conservation. So for example, when we had two unknowns, we had, let's say we were looking for two final velocities, and we were given the two initial velocities and the masses. So in order to solve, we had to use both these conservation statements, and we solved using a system of equations with substitution. It was a rather long problem. And let's see if under specific circumstances, the circumstances of a head-on elastic collision, so that we only have motion in one dimension, if we can find a shorter way of solving. So before, we might have mass and velocity given in the before situation, and in the after situation, we're looking for the final velocities. So that's the very last, the more challenging problem that we did in B8. So first, just to talk about what do we mean by a head-on elastic collision in one dimension. So it means that the incoming and outgoing velocities are in line with a center-to-center line between the two objects. And all of this is going to happen in one dimension. So 2 dimensions is coming up. So these two initial velocities are not necessarily the same velocities, so that's just worth noting. In fact, it's possible that one initial velocity is 0. So that's worth mentioning. And this is all, once again, in one dimension. So the actual definition from your textbook is a head-on elastic collision is an impact in which two objects approach each other from opposite directions and momentum and kinetic energy are conserved. So this is in contrast to what's coming up in a few videos. There's a glancing collision. So 2D is coming up soon. That would be if this golf ball was heading in this direction and hit this tennis ball here and kind of flew off in that direction. So and then the tennis ball would maybe fly off in that direction. So it's adding another dimension to these problems. So we're not doing that yet. Head-on elastic collision, HOEC, it's kind of a mouthful. So just an FYI, I might say HAWK when I mean these special conditions. So when momentum and kinetic energy are conserved, we can write those two statements, and those equations can be manipulated and combined to have simplified equations for final velocities under the specific elastic and one-dimensional conditions. So if you look on your textbook on page 240 and 241, you can see the derivation of these equations, but this should be great news. So you have these equations that are ready for you to substitute in your masses and initial velocities and solve for your final velocities. So this is the equation, or the equations that you've been waiting for. Notice that if one of the objects starts out with 0 velocity, so let's say if velocity 2 was 0 initially, this whole term goes to 0 and it simplifies even more. So let's try an example. And just reading the example before we start, we've got a 2 kilogram cart moving at 8 meters per second to the right, strikes a 5 kilogram cart originally at rest. The collision is elastic. Find the velocity of each cart after the collision. Maybe there's some deja vu here. Maybe there's some deja vu here. So we've already solved this exact problem last lesson, the long way. So let's solve using our new Hawk equations. But wait, stop. Before you use the Hawk equations, check to see if the conditions apply. So we are assuming, well, based on the diagram, this shows a one-dimensional, so head-on collision, and it does say that it is elastic. So the Hawk equations apply, and we can move forward with those equations conveniently. It also says that one object starts from rest. So that's even better news. So let's take a look at this problem. We draw our before diagram, label the masses and initial velocities, and then we are looking for the final velocity of object 1, and we have our new Hawk equation. The entire second term cancels to 0, and we substitute in our masses. It's really important to note that I've just written it for magnitudes because we are in along one dimension, but we should be watching for positive or negative velocities depending on direction, because even though it's in one dimension, you could be heading east. This could be heading east and this could be heading west. So 8.0 meters per second right, we would call right positive. It happens to conveniently be that we have a velocity of 0, so we don't really have to have a negative in this, but we may have to have a negative at some point. So we get 3.4 meters per second, negative 3.4 meters per second. What does that negative mean? It means that it's in the opposite direction as that positive, the positive 8 meters per second. We said right is positive. So we should actually draw that on our diagram somewhere over here or here where it's visible. What direction is positive. And then when we do the same thing for the second velocity, it's just a matter of substituting in the number, so you can see how convenient, how much more convenient this equation is than doing it the long way in B8. And notice that our answers are the same answers as we got using our other method. And look at the directions, they're opposite to each other. We check our common sense. We do our common sense check based on the diagram, and it does make sense, the direction those arrows are facing. Okay, so as I mentioned before, when one object is at rest, the Hawk equations simplify even more. So not only could one object be at rest to have sort of like a special simplified case, we also have these other special cases that we're officially going to go over now. So if the two objects have same masses, it's going to look like they just switch velocities. So let's take a look at that using the little interactive that I've been encouraging you guys. These are just screen captures from those, from the interactive. So when two colliding objects have the same mass, so I set them both to 2 kilograms, then the final velocity equations can be manipulated to discover that VF1 equals VF1 is VI2 and VF2 is VI1. So it appears that the objects just switch velocity. This red object had 4 meters per second right velocity before, and then after it's the blue cart that has that velocity. So it appears as though they They switch places. I highly discourage you from memorizing the special cases, and instead I want you to just go back to the original, the Hawk equation, and see if it makes sense to you each time. So if masses are equal, m1 equals m2, this numerator is going to be 0. The whole term here is going to be 0, and you just get this. Then we can simplify it more. M1 is equal to m2, so this simplifies to 2m over 2m, and oh dear, that should say VI2. So VF1 is equal to VI2. So just to clarify, VF1 equals VI2 and VF2 equals VI1. So they switch velocities. So we have another special case, and this is, I guess, the most intuitive of the cases. So let's say if we have a fast-moving light object hitting a very heavy stationary object. That light, fast object is just going to essentially bounce off with little or no change in velocity, but the opposite direction. So that's another one. I encourage you to pull up the Hawk equation and see how you can prove it mathematically through simplifying. Okay, let's try an example. So we've got two chunks of space debris collide in a head-on elastic collision. One piece of debris has a mass of 514 kilograms and is at rest. The other chunk is a mass of 1.27 kilograms and is traveling at a velocity of 12.7 meters per second to the right. What are the final velocities of the two chunks? The first thing I notice is it says head-on elastic collision. So right away I'm working with the Hawk equation. Then I might notice that this mass is a lot bigger than the other one, and it is stationary. So this is actually one of those special cases, although we could still solve it without recognizing the special case at first. Oh, there was a part B of the last example, and one term didn't fully cancel to 0. We subbed in 1.5 meters per second. So actually just taking a step back to go to that. So initially, if the blue cart was going to the right and the red cart was at rest, this whole term cancels and we're just left with this piece of the Hawk equation, or one of the Hawk equations. But if that is not true, this is going in to the left. I knew there was a reason why I was stressing the direction. So that would be, oh, here we have our designated positive direction. To the left would be negative. So we're going to substitute in for part B the exact same equation, but we're going to, when we get to the second term, it's going to be negative 1.5 meters per second, and you'll get a different, faster velocity of object 1. And a faster object, a velocity of object 2. That should make sense because there's more initial kinetic energy in the before diagram. So we have our final answers for part B with the right sig figs, units, and direction. So going back to that space collision, we write out our Hawk equation because it says head-on elastic, and since the larger object is at rest, or the first object is at rest, this entire first term goes to 0. And we can solve using the remaining term. We get 0.0049, which is basically 0. So we can say the final velocity of the second object, that heavier object, is 0. And the initial velocity is essentially the same speed but opposite direction. So you would conclude 12.7 meters per second to the left and 0 meters per second. I highly encourage you to look at and check if you can see for any other special cases using these interactives. So now we're going to talk about collisions with cushioning. So maybe this is the case where you have a bumper or a spring that is going to absorb the on impact. So when two objects collide and one or both have compressible bumpers attached, the time of contact between the two objects is increased as compared to a collision without bumpers. This occurs because during the collision, the bumper compresses and then springs back to its original position. So we're still talking about conservation of the energy. So during the compression, so here you have a graph of total kinetic energy in blue and elastic energy in green. And this is over time, as the yellow car and the blue car are heading towards each other, and one of them has a bumper, a spring bumper. So there's a lot of kinetic energy at the beginning, and then when they approach each other as the bumper starts being compressed, that kinetic energy decreases as the elastic energy increases, and then there's a maximum elastic energy. And that elastic energy, as the spring springs back, it starts transferring that elastic energy back into kinetic energy. Yeah, so during the compression, kinetic energy converts to elastic potential, and then the potential is converted back to elastic on the rebound. So if the compression of the spring bumper during the collision is X, then you can write the law of conservation of energy like this. So the kinetic energy before equals the kinetic energy after plus the elastic energy. And there's a title covering the words, so I can't see the beginning. I'm assuming that says, as the bumper compresses, elastic energy increases and the total kinetic energy of the two objects decrease. The total mechanical energy remains constant. So if you were to add up the green and the blue at all points, it would be a flat line. As the compression decreases, the elastic energy decreases and the total kinetic energy increases. We see the total mechanical energy remains the same throughout the collision. If you have to determine the maximum compression, X, then you can use the momentum equation simplified in this way, because at the moment there's maximum compression, the two carts have the same velocity. And this is less intuitive. So you'd think maybe they're both at a point of zero, but they're actually not. So if you imagine a graph starting from object one velocity from where it starts to where it's going, and then object two has the graph of where its velocity starts heading towards where it's going, there is an intersection point, and that intersection point is where you would find your X. So the intersection is not necessarily at zero. It's when the intersection point is whatever it is, whether it's zero or not. So the first step in these problems would be using momentum to solve for velocity and then subbing in your missing velocity into energy. So we're going to do an example to show you how that would look. So in this example, we have a cart with a mass of 1.8 kilograms. So that's cart one. And it's moving with a velocity of 4 meters per second to the right along a frictionless track. Cart two has a mass of 2.2 kilograms and is moving at 6 meters per second to the left. The carts collided with each other in a head-on collision. So that's good. That means there's an assumption that it's elastic and it says head-on and it's along a track, so that's 1D. So we've got a Hawk equation potential to use here. If we're talking about velocities after, but we're actually looking for information during the compression. And so this example, the focus is on what's happening during that compression point. We usually draw a before diagram quite early before they hit each other, and the after diagram quite late after they've hit each other. But in these cushioning examples and the practice problem that you're going to do, we're looking at as that bumper is being squished. or as it's being crumpled and then returning back to its original shape. So determine the compression of the spring during the collision when cart 2 is moving 4 meters per second to the left, and then calculate the maximum compression of the spring. So I'm hoping that you can see the PDF. Okay, I'm hoping that you can see example 1 and the diagram I've drawn to outline the givens. We're going to use conservation of momentum first to isolate for VF1. So we didn't have to use a complicated equation with energy yet to find VF1. Once you find VF1, you have everything you need. You don't have 2 unknowns. So you find VF1, then you sub that. That's a velocity. Negative gives you the direction, but we're going to sub in the positive version into the speed point of the conservation of energy statement. So this is the conservation of energy statement if you have cushioning. So the 1/2 kx squared is the elastic potential energy. So we have everything except x. Originally, we didn't have the F1, which is why we knew we had to solve it. That's why we had to go to the momentum equation. Then we can solve for x, and we get 0.02924 meters, which means the compression is 2.9 centimeters. Okay, so I encourage you to experiment with these interactives that I linked to at the bottom of this video, and they do go over. You'll have to input the special conditions to see those special cases. And as well, this one is getting into 2D collisions, which is coming up next. So if you want to explore it before we actually go over the lesson, that is a good one to go to. So now it's time for you to do some practice questions. So most of these are on the practicing using the Hawk equations, but just always double check that the conditions, the criteria of the Hawk equations are being met, because in the future you'll have these questions mixed in with other equations where the equations are not applicable, and that's where a lot of mistakes can be made. So make sure you always confirm that that you're allowed to use the Hawk equations. And as well, don't forget to submit the Google Classroom tasks. There's a B9 exit ticket, and submit the practice problems that was on the previous slide with the posting where you got this video. And one important question, is this the first lesson Miss Cornacchione gives without a cat in the slides? Nope. There's the cat, Mike DeAngelis, in the background with an electric guitar. I must have gotten my PowerPoint slides of my favorite band mixed up in my collision slides. So sorry about that. We'll just go back to our collision slides. Okay, so let's do some practice questions. Remember to submit, and I've put a direct link to those interactives below. Have a great day.